Okay, let's go on with Faraday's law 33.5. And Faraday's law is going to help us with understanding more about induced currents and induced EMFs. We saw previously that we can have a fixed magnetic field and a coil that is moving through the field, and that will induce a current in the coil, and also an EMF is induced with that current. We saw in Faraday's experiment that when you have a coil that is fixed and you bring a magnet close to it, the changing flux induces a current in the coil. So this means that there are two effects that we can identify. One where we have a fixed magnetic field and a coil that is moving in the field, a current is induced. And the second effect is that you have a fixed coil, a magnet is brought through the coil, so the changing flux in the coil induces a current in the coil. So this is what we're going to look at today. So I'll just remind you of what we had last time. So we saw previously that a coil moving in a magnetic field had a current induced in the coil, and we can say this current is due to the action of magnetic forces on the charges in the coil, and we can say that this was what we call the motional EMF. So we can say that the current induced in this coil and its associated EMF is due to the changing magnetic flux. So we can say I induced is equal to the EMF divided by the resistance of the conductor in the coil, and the direction of the current is given by Lenz's law. So the magnitude of the EMF was found by Faraday, and this is what is called Faraday's law. So the EMF induced in the coil was discovered by Faraday, or in some books you might see it this way: EMF is equal to minus the change in flux with respect to time. In our book, this is what we have, but you may see it in other books that way. So this is called Faraday's law. Okay, the statement of the law is as follows. We can say that an EMF is induced in a coil if the magnetic flux through the coil is changing. And we can say that the magnitude of the EMF is given by, and the direction of the EMF is found by using Lenz's law. So the direction of the EMF is in such a way as to produce an induced current in the direction given by Lenz's law. So this assumes that we have one coil. So basically an illustration of what we have. So let's say we have our coil again, just like we had before. So this is a coil of wire, and you plunge a magnet into the coil. This is north and that is south. If the magnet is going this way through the coil, we know that the field lines are that way. So if the magnet is going through the coil, then the current, the flux through the coil is increasing, going down. So the current is induced in this way so as to produce a magnetic field which changes in a direction as opposed to the flux causing it. So the current is going that way. The EMF induced in the coil is given by the absolute value of the change in flux with respect to time, as we know. And the EMF, of course, is equal to the current times the resistance to the coil, where I is the induced current, okay, and R is the resistance of the coil. So for N coils, we can write the EMF to be equal to N d phi dt. So if you have a N coils, then you write this. So we can use this idea of changing flux to arrive at the induced EMF in the same way that we did with motional EMFs a few chapters ago. Let's look, for example, at what we have here. So let's use Faraday's law in the example below. So we have our magnetic field again, and we have a coil like that. So we put a bar on this coil that way. So the bar is moving to the right with a speed v, and the length of the bar is L. So let's say that it has a length L, like that. And so we know that there's a current induced in the coil which goes this way. We've already seen something like this already, so the current is induced that way. So if you imagine putting this on a coordinate system where this distance is x, then we can say the flux through the coil is given by the magnetic field B times area A. Okay, the magnetic field B is into the board, as you can see, and the area vector is also parallel to the field. So the magnetic field, the flux is given by B times A. And we also know that the EMF by Faraday's law, so let me write that down here. So before that, we can say A is equal to the length of the coil. And let me shorten that coil so that we are saying that the length is just the length that is encompassed by the bar. Hold on a second. Let me shorten it a little bit. So we are talking of this length here. So that is L. So the area is equal to L times X, where X is changing. So X is moving, increasing as the bar goes to the right. That means that the area is changing, which leads to a change in the flux through the coil. So by Faraday's law, the EMF is equal to the absolute value of the change in flux with respect to time, where the flux is of course equal to B L times X. So the change in flux with respect to time is equal to B L dx dt. So the EMF can be written as B L V, where dx dt is equal to V. Okay, so we can say that V is equal to dx dt, and the change in flux with respect to time is just equal to the EMF. Any questions on that at this point? I've dropped the absolute value because we are dealing with positive quantities. So then, since the EMF is equal to current times resistance, so the current induced times resistance, then this should be equal to BLV. Therefore, we can say that the induced current is equal to BLV divided by R. So V is speed, R is resistance of the coil, and L is the length of the bar. So that's the length of the bar moving, and B is the field strength. So this result is the same as what we had a few chapters ago with motional EMFs. Okay, so you can see that we can get the same result using Faraday's law. So Faraday's law tells us that there are two things that can happen. So let's look at the feature of Faraday's law. So a feature of Faraday's law is that we know that from the law, the law tells us that EMF is equal to change in flux. Change in flux with respect to time with absolute values. And so where the flux is equal to B times A, assuming that B and A are parallel to each other and point in the same direction. So since we are saying that B and A point in the same direction and are parallel to each other, the flux, is equal to B dot A. So we are just saying that's equal to B times A, since they are parallel and point in the same direction. And so since that is the case, we can just say that the EMF can be written as the absolute value of d dt of the flux, which is the magnetic field B times A. Okay, and we can expand this to say that d dt, so we can put A out if you like. Now let's do the A out first. So we can expand this by saying, actually let's do this with B dA dt plus A dB dt. Okay, so that's your EMF. So Faraday's law tells us that an EMF is induced when we change the area of the coil with respect to time while keeping B fixed, or we change B with respect to time while keeping A fixed. Okay, so we can induce an EMF by 1, fixing B and changing A, area A, and 2, fixing A and changing field B. So those are two things that are possible when you are dealing with Faraday's law. And if the field is not changing, then we just take away the dB dt, or if the A is not changing, we take away the A dt. So it becomes pretty straightforward. Any questions on this? We will do examples near the end when we have some time for that. So let's go on to the next section, 33.6, induced fields, because there is still a problem. We still don't know how the current is induced in this particular situation where the coil is kept fixed, but the magnetic flux is changing. So we'll look at that in the next section. So in this section 33.6, we have induced fields. So we will say that in the previous sections, we saw with motional EMFs that if a coil is changing in a fixed magnetic field, the magnetic forces on the charges in the coil will cause current to be induced in the coil. And so we know how current is induced. In the case of Faraday's law, when the coil is fixed and the magnetic flux is changing, it's not clear yet how the current is induced in the coil. So that's what we need to look at. So we'll say that in Faraday's law, changing magnetic flux induces current in a fixed coil. So having a current present means that there's an electric field which is driving the current through the loop. And this electric field is an induced electric field which is in a direction so that it causes the current to be produced or the induced current to be present in the coil. Okay, so this is what we are looking at next. So we can say that the current induced is due to an induced electric field. So we shall call this induced electric field, let's call it E. This electric field is present in the space whether a conducting coil is present or not. So the induced electric field caused by the changing magnetic flux. So we can calculate the induced electric field as follows. So we can say that because current is the flow of charges in a conductor, the charges moving around a closed path are forced by the presence of the electric field. So are forced by the electric force F equals Q times E. So let's say we have a magnetic field like that. The magnetic field is changing. So if the field is changing, then what we have is if we put a conductor in here, then we can say the current in the conductor is in such a direction, this way. And this current I is because there's an electric field this way, which is driving the current. And when it comes here, there's an electric field E that also drives the current and so on. So another electric field. So this electric field also drives the current. And so from there, we've already said that the conductor doesn't need to be present. So we can take the conductor out and just show that if you have a magnetic field like that and you have and there is a conducting loop or there's an electric field in that space, that electric field is going to go through the entire space at different concentric circles like that. So you have different field lines this way, tangent to each of those imaginary loops this way. Okay, so this is with conductor present. So with conductor, you have a current I. So these are all just E. These are electric fields E with conductor and without conductor. And we are saying that if you are driving current through a conductor, the force that drives the current is given by the charge times the electric field E. And we are saying also that the induced field from Faraday's law, the EMF, also EMF is equal to the work done per unit charge, or EMF is equal to W over Q, like that. And so we can use this. So we know W is equal to F ds. So dW, the element of work, is equal to F dot ds. Don't forget these are all vectors, of course. So we can say the work done in a closed loop, closed electrical loop, like what is present in the magnetic field, is equal to F dot ds, where this is the work around a closed loop. And that closed loop is the loop that I've shown you here. That is the loop where the conductor is placed. If the conductor is present, then the current is being driven through that loop by a force F equal to Q times E. So we can say W closed loop is equal to the integral. And remember, this circle I've put in the integral sign means it's a closed loop. And F is equal to QE dot ds that way. And so from there, we can say that using the EMF definition, EMF is equal to work in the closed loop over the charge Q. So if you write it that way, then we can say EMF is equal to the integral of E dot ds, which can then be written as absolute value of d phi dt from Faraday's law, where we note that phi is equal to B times A. Therefore, since we are saying that B is changing, since B is changing and A is fixed, then we'll say that the EMF is equal to the integral over the loop. Don't forget the loop sign, E dot ds, and that's equal to A dB dt, like that. So this is an Amperian version of Faraday's law. In some books it's called Ampere's law, and it's less like what we did with the Amperian loop. Any questions on this at this point? So let's look at an application of this where we look at the induced current in a solenoid, okay, or in a loop that looks like a solenoid. So let's see. Okay, so let's look at an example of the electric field due to a changing magnetic field in a solenoid. So determine the magnitude of the induced electric field. So let me draw a picture for us. So let's say we have a solenoid this way, and we have current going through this way. So if the current is going through that way, then the field is this way. So we got a field that way. And so in this field, then, because the magnetic field is changing, it induces an electric field. And so you can think of the field lines that way in the solenoid. And so what we have is the field lines will be going that way, because the current is induced in such a way as to oppose a change in flux. So you can think of it this way again, where we have our electric field that way. Since the current is this way, it means the electric field lines are that way. Okay, so we have field lines this way, that way, this way, and that way, E, like that. So this is a loop of radius R, and we are saying that at some point here, this is an element ds. So by using Ampere's version of Faraday's law, EMF is equal to the integral over the closed loop of E dot ds, and that's equal to d phi dt. And so the loop involved is given by E integral of ds, which can be written as E times 2 pi r, because the loop is just the length of the loop is 2 pi r, and this should be equal to A, which is the area of the loop, dB dt. So the electric field induced is equal to A over 2 pi r dB dt, where A is equal to pi r squared. And so we can say E induced is given by pi r squared. So we have pi r squared over 2 pi r dB dt. Actually, let me keep the absolute value signs there. Don't forget that. And this can be written as R over 2 absolute value of dB dt. Don't forget that B is a function of time. So at some point, we shall use this version of the formula to calculate different things. So R over 2 dB dt. So let's continue with that example. We will say, as an extension of this example, we can say that suppose the current through the solenoid is I of t equals I naught cosine omega t. So we can say write an expression for the induced electric field. So let me redraw this solenoid for you again. Okay, so the current in the solenoid goes this way. Sorry, it's the other way. Let me do it again. So the current is going this way and coming out that way. So the field lines are this way and that way. So inside the solenoid, we're going to have a loop like that, which is the loop where the electric field is going to be pointing this way. Okay, so this is the E field that way. So if you see that the field is going up, then according to Lenz's law, the induced electric field is in such a way as to produce a current that opposes the field. So since the current is going down this way, then in the loop, it shows that the current should be going along the loop that way. So the electric field is pointing this way along the loop. That's why I've drawn it that way. So you're going to have a current going this way in the loop and that way. So this loop has radius r, which is what we've done already. Let me remove that because it's too tiny. You can't actually see it. So I'm just saying that this current in the solenoid I of t is given by I of t equals I naught cosine omega t, and the solenoid has n turns per unit length. So use that information to write an expression for the induced electric field in that solenoid using this formula that I've given you up here. So let's try that and then we'll go on. So we start with the induced EMF, the induced electric field is equal to R over 2 dB dt, like that. So this is your starting point. And then you're going to say that B for a solenoid, what is the magnetic field for a solenoid? Remember the formula for B for a solenoid, what did we have? Mu naught N I of T. Or that's I for the solenoid, and basically this is your I solenoid, okay, where the solenoid is equal to I of T, all right, which is equal to I naught cosine omega t. So this is what I wanted you to do. So then you write that the magnetic field of the solenoid is equal to mu naught and I naught cosine omega t. So that will be your magnetic field that you're going to use. So you can now continue and finish that so that we can go on. So E induced is your induced electric field. So what is the answer for E? Did anybody complete it? When you do the derivative of D, what do you get? So this is what you should end up with for the induced electric field in the solenoid. So there's one step that I should put here. So E induced then is equal to R over 2 D, and then we can have d dt of B, which is equal to mu naught and I naught cosine omega t. And with the absolute value sign, you can take the negative away if you want. So let's remove the negative. If we can take the negative with the absolute value sign, so that becomes a positive. So without the negative, without the absolute value, you will still have a positive, because in the other formula I gave you, E is equal to minus d phi dt in some books. So if we didn't use the absolute value, we'll still end up with the same result as what others would have in a different book, because they define the E as minus d phi dt. Okay, so that takes away the negative sign. So in our case, since we're using absolute value, the negative goes away. So we have the positive. All right, so let's look at in 33.7. These are applications. We can apply our knowledge of induced currents to the electric generator. I know some of you will be working on electric generators for your project, so let's look at this to the electric generator, and then we can also look at a transformer. There is also the application to metal detectors, but we'll leave that for now, and we'll look at the generator. So the generator consists of a coil of wire in a uniform magnetic field. We can say that the coil is rotated by mechanical means in the magnetic field. And we can say that the changing flux induces an EMF and a current. So we can use our knowledge of Faraday's laws to determine what that induced EMF would be. So we're going to find induced EMF and induced current. So let's take a magnet. Let me see if I can draw a good magnet like that. So let's say this is N, and then we can draw the south magnet this way. Let's say this is south, And then we'll put a coil in the magnet. And let's draw this coil this way. So we'll draw the coil like that. And so let's say the coil is rotating this way with angular velocity omega. Okay, so the flux through the coil is that way. So this is your magnetic flux going through the coil. And so at this point, this is the area vector A for the coil. Okay, and this is an angle theta. I'm sorry, it's getting small. Hold on a second. Let me see if I can do it again. So this is the flux again through the coil. And let me use a tiny fine point here. So I'll say that there's an area vector A that way. And again, we have a flux at this point this way. So the angle here is theta. Okay, so this is B. There's a magnetic field B. So this is all B. So this coil is being rotated by some mechanical means, whatever that happens to be. Perhaps you have a turbine, water turbine, or wind turbine, anything that's rotated, or a hand crank mechanism. You can be rotating the coil by some mechanical means, and as it's being rotated, then the current is going to be induced this way. So we can say that by Faraday's law, the EMF is equal to N d phi dt, where N is number of turns of the coil. And if it's just one coil, then we shall use N equals 1. But let's assume that there are N turns of the coil. And so we can say that the flux through the coil is given by the magnetic field B times A, B dot A. Let's say B dot A, where flux can then be written as B A cosine theta. And we've said that the coil is rotating with angular velocity omega. So since the coil rotates with angular velocity omega, we have angular velocity omega equals the change in angle with respect to time. Therefore, theta can be written as omega t. And so we'll write that the flux through the coil is B times A cosine omega t. And then we'll say that the EMF induced is equal to N and then d phi dt, which can then be written as N d dt of B A cosine omega t. Can you complete it to get EMF? So EMF induced is therefore equal to what? So calculate it and tell me what you get for the EMF. So this is what you should end up with for the EMF induced, N times B times A omega sine omega t. This is induced. Now let's find the induced current, assuming that the coil has resistance R.
And it's positive, right?
Yes, it's positive since we're taking the absolute value. That's right, yeah. So assuming the coil has a resistance R, so what is the induced current? Induced current is the induced EMF over the resistance. Induced EMF, you remember, is just the same as a potential difference. Okay, so this is the potential difference induced in the coil. It's an oscillating potential because the coil is rotating. So if you take a hand crank generator and you crank it with a coil in a magnetic field, if you connect a bulb to it, the bulb is going to light up, but there's a current, you have a current going through the bulb, so the current will oscillate in the bulb, so it will flicker a little bit. So what do we have then for the induced current? You can just see what it should be. We know what induced EMF is, so what is induced current? So that's your induced current, is the induced EMF over R. So if you plot a graph now of time, then you're going to see that you have a EMF that goes like that. It's a sine. Induced EMF goes this way, of course. And then you're going to have your induced current that way. Okay, so this is the induced EMF, and this is your induced current. Okay, so you can see they are both sine waves. So let's go on. Actually, one more thing. We can take I naught to be equal to N BA omega over R, so that we shall say that I of t induced is equal to I naught sine omega t. And that's what we have. There's a sine curve, and the same applies for the induced EMF, and BA omega can be written as E naught. Okay, so similarly, NA B omega is equal to E naught. So we'll say that E of t is equal to E naught sine omega t. So then I can now write this as E naught, and this is now I naught. So those are the amplitudes. Okay, and this is minus E naught, and this is minus I naught. All right, so at this point, I'll stop.